Dear students, in the present class, we will introduce another violation of the classical linear regression model assumption, namely the assumption of no autocorrelation. As we have explained earlier, in econometrics we use three types of data: cross-section data, time series data, and panel data. And we have also developed the classical linear regression model on the basis of 7 assumptions. But these assumptions will not hold in all types of data. For example, as we have discussed in the previous classes, the assumption of homoscedasticity will be violated in the case of cross-section data. As we have said, heteroscedasticity is a rule rather than an exception in cross-section data. But in cross-section data, we do not expect that successive values of the error terms will be autocorrelated. If we observe such a correlation between successive values of the error terms, then there is what is known as spatial autocorrelation. Partial autocorrelation. That means if we take a cross-section of households, spatial autocorrelation means if there is a disturbance associated with the consumption-income relationship of a particular family, it will affect the consumption-income relationship of other families also. In general, we do not expect it. But in time series data, successive values of the error terms will be autocorrelated. Successive values of the error terms will be autocorrelated. This is known as the assumption of autocorrelation, also known as serial correlation. The assumption of autocorrelation, also known as serial correlation. So in time series data, we cannot expect that there will be no autocorrelation. In most cases, the assumption of no autocorrelation will be violated in the case of time series data. And if the assumption is violated, we have what is known as autocorrelation, or what is also known as serial correlation. Now, what are the consequences? As we have discussed earlier, if there is heteroscedasticity or autocorrelation, OLS estimators are no longer efficient. That is, OLS estimators are no longer blue. What is blue is GLS. What is blue is GLS, generalized least squares discussed in the context of heteroscedasticity. So, the usual T, F, chi-square, etc. testing procedures are not valid, as in the case of heteroscedasticity. So, even if there is autocorrelation, it will not affect the unbiasedness property, consistency property, etc. of the estimators, but the minimum variance property will be affected. What is efficient or minimum variance estimator is GLS, not OLS. So the conventional hypothesis testing procedures are not valid in the presence of autocorrelation, as in the case of heteroscedasticity. Now let me give a formal definition of what is autocorrelation. The term autocorrelation may be defined as correlation between successive members of the series of observations ordered in time. Autocorrelation may be defined as correlation between members of the series of observations ordered in time, as in time series data, or in space, as in cross-section data. So it is correlation between members of series of observations, or it is correlation between successive values of the series of observations ordered in time or in space. Now, if there is no autocorrelation in the regression context, the assumption of no autocorrelation is that covariance ui uj given xi xj is equal to 0. The classical assumption is covariance ui uj given xi xj is equal to 0, I not equal to j. What we say is, suppose that we are using time series data on consumption and income, and suppose that this is the PRF. So this is corresponding to x is equal to x1, x2. We have a series of y values, and u is nothing but y minus expected y. So the assumption of no autocorrelation means there is no correlation between ui and uj given xi and xj. This is the assumption of no autocorrelation. And the blue property, the Gauss-Markov theorem, is based on this assumption. But when we deal with the time series data, in most cases this assumption will be violated. As an example, suppose that we study the relationship between output and inputs. Suppose also that we are using quarterly data. Now, the assumption of no autocorrelation means that if there is a disturbance, a strike in the first quarter, for example, it will affect the production relation, the production function. The assumption of no autocorrelation means this disturbance will not be reflected in the second quarter also. But if the effect of a disturbance is felt in the next quarter also, that is, the production will not be normalized, will not become normal. In the second quarter also, we have a situation of autocorrelation. Or consider the case of, or consider the consumption-income relationship. Now, if there is a disturbance in the consumption-income relationship of a family this quarter, and its effect is felt in the next quarter also, we have autocorrelation. Otherwise, we have no autocorrelation. So remember this, heteroscedasticity is generally expected in cross-section data, and autocorrelation is generally expected in time series data. So if you are using time series data in your regression analysis, once the model is estimated, you must always check for whether there is autocorrelation or not. Now, before proceeding further, let me clarify a few more points about, and in terms of notation, if there is autocorrelation, we write covariance ui uj given xi xj is not equal to 0. This is the assumption of, this is what is known as autocorrelation. This is what is known as now autocorrelation. Now, to give a little more information about what is autocorrelation, suppose that a model has been estimated, and suppose also that the residual is observed, and suppose that I plot this residuals as u hat 1, u hat 2, u hat 3, u hat 4, u hat 5, u hat 6, 7, 8, 9, 10. Suppose that my sample is based on 10. Actually, autocorrelation means autocorrelation corresponds to population disturbance terms. But population disturbance term is unknown. So all our inferences about autocorrelation, heteroscedasticity, etc. are based on the residuals, assuming that residual is a good estimator of the error term ui. So the model has been estimated, and using this I formulate two series u hat t and u hat t minus 1 like this, u hat t and u hat t minus 1. Suppose that we know that the residuals may be positive or negative. Suppose that the signs are like this, like this. So if I generate two series, u hat t minus 1 start with the u hat 1, u hat 2, u hat 3, u hat 4, then u hat 5, u hat 6, u hat 7, u hat 8, u hat 9. Then t starts with the u hat 2, u hat 3, u hat 4, u hat 5, u hat 6, u hat 7, u hat 8, u hat 9, u hat 10. When we lag the series, one observation will be lost. Now, let me give the signs. U hat 1 is, as you can see, positive, 2 is positive, 3 is, 4 is positive, 5 is positive, negative, 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 negative. Then u hat 1 is positive, 2 positive, 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 negative, 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 negative. Now let me plot this as u hat t minus, u hat t minus 1. And the concept of correlation was explained in detail where I have divided the XY plane into 4 quadrants, and now the u hat t minus 1 is divided into 4 with the 0 as the intersecting point, because it is a zero mean process u hat t, as we have studied earlier. Sigma u hat t is 0, so u hat bar is also 0. Now if you plot u hat t minus 1, the first two are positive, again positive, again positive, positive. Then u hat t is negative, u hat t minus 1 is positive. One observation here, all the others are negative. U hat t is negative, t minus 1 is also negative. Now, if you plot the observations taking u hat t and u hat t minus 1 like this, and if most of the observations lie in these two quadrants, we know that autocorrelation or correlation is positive. Correlation is positive. Now suppose that I adopt a different strategy. 0, time. I plot u hat t, that is these observations as a time series plot. And we know that the first 5 observations are positive. Then negative, like this. Then again positive, etc. Like this. Now, from this observation, we can conclude that if the sign of the residuals here as an estimator of the error term, if the sign of the residuals do not change frequently, it is an evidence of positive autocorrelation. Evidence of positive autocorrelation. Now this is clear. Or if you plot u hat t against time, you will get a 0. You will get a pattern like this. Many positive followed by many negative. Again many positive followed by many negative, like that. Now suppose that this is a plus, this is a minus, plus, minus, plus, minus, plus, minus, plus, minus. The signs change frequently. This is minus, plus, minus, plus, minus, plus, minus, plus, minus. And this is plus, minus, plus, minus, plus, minus, plus, minus, plus, like this. Then u hat t is minus, u hat t minus 1 is plus. So where is that point? The point is here. Then here, then here, then here, then here, like this. So if the observations are like this, from our earlier analysis, it is evidence in favor of negative autocorrelation. So if you plot u hat t against time, positive followed by negative, again positive, again negative, positive, etc. If the disturbances are changing the signs frequently, it is evidence against, it is evidence in favor of negative autocorrelation. In the time series plot, if the disturbances change the signs frequently, it is evidence in favor of negative autocorrelation. Now, which pattern shows no autocorrelation? Suppose that the patterns are like this. There is a plus, 2 minus, then plus 3, 1 minus, a plus, 1, 2 minus, etc. No pattern is observed. And if you give signs to u hat t and u hat t minus 1, you will see that the observations will lie in all these quadrants. Observations will lie in all these quadrants. It is evidence in favor of no autocorrelation. Evidence in favor of no autocorrelation. So autocorrelation in econometrics means correlation between successive values of error terms. Autocorrelation is correlation between successive values of the same variable, whether it is x, y, z, or whatever it is, because it is a kind of correlation where we consider correlation between successive values of the same variable. That is why the name autocorrelation. In econometrics, we use this term to specify correlation between successive values of the error term, denoted as expected ui uj not equal to 0. Now, it is possible that autocorrelation may be positive or negative. But in econometrics, in most cases, you will encounter positive autocorrelation. Autocorrelation can be positive or negative, but in econometrics, in most cases, you will encounter what is known as positive autocorrelation. So if there is autocorrelation, it will be positive in most cases. So remember this graph in your minds. It will be a guide to determine the nature of autocorrelation. Remember this, if the signs are not frequently changing, it is evidence in favor of positive autocorrelation. If the signs of U hat is frequently changing, it is evidence against, it is evidence in favor of negative autocorrelation. If you cannot obtain any pattern, it is an evidence of no autocorrelation. Autocorrelation can be positive or negative, but in most cases it will be positive.